Hello everyone, welcome back to my channel. In our today's video, we will be learning about the basic concepts of D block element, including their electronic configuration to the oxidation state, what is the definition of D block elements, why they are so called transition elements, is the transition elements and D block elements the same thing or they are different? If they are different, in what way they are different? So these are the basic concept which we'll be trying to learn in our today's video. So let us go on into the first and the important part of this particular video is what are D block elements? How we can understand that which elements are called D block elements. To understand that, let us try to analyze our periodic table. Okay. So if you see the periodic table, in this periodic table, you can see that the middle block, okay, which is situated in between S and P block elements are nothing but actually the D block elements. Why do we call them D block elements? Remember that the last electron in this element, okay, in this block, which is situated in between the S and the P block, whenever you talk about the last electron, it goes into the D subshell. Similarly, why do we call it S block? Because the last electron goes to the S subshell. And whenever we talk about P block element, the last electron goes to the P subshell. And similarly in the F also. So whenever we talk about D block elements, remember that the last electron goes into the D subshell. That's why we call it D block elements. But remember that if you define what is S block and P block element, how do we define S block elements are those elements in which the last electron goes to the S subshell of the ultimate energy level or the valence shell. In P block also, we define in the very same way that it goes into the P subshell of the valence shell. But when we come in case of this particular D block element, we don't say that it goes to the D subshell of the valence shell. Remember that it goes to the D subshell of the penultimate shell, that is second last shell. Now, why it is so? Okay. If you see the configurations, okay, how do we write? First, we start from hydrogen, then helium, then lithium, beryllium, boron, carbon, as we go on. Okay, sodium, magnesium, you can see in the screen, aluminium, silicon, phosphorus, sulfur, argon. Once we reach argon, in argon, what we fill is 3p, 3p6. It is the fully filled p orbital, right? After 3p, remember that we don't fill 3d. Okay, so since 3d actually has a higher energy than 4s, so first 4s is filled. So in potassium, we fill 4s1. In calcium, we fill 4s2. Then when we come for scandium, we fill 3d. So try to understand that what we have done is when we talk about D block element, the valence shell will contain 2 electrons only, no doubt, 4s2. What we are filling or what we are expanding is the inner shell, that is 3. Okay, the third shell where the electron goes from 8 to 18 when we fill 10 electrons in this D block. So remember that in case of D block element, we don't fill the valence shell, we fill the penultimate energy level, that is the second last energy level. Okay, we expand the second last energy level, not the ultimate. The ultimate energy level will, or the valence shell will always contain 2 electrons. So the number of valence electron in D block elements is 2. And what we fill is the second last or the penultimate energy level where we expand it from 8 to 18. Okay. So that is why we say that D block elements are those elements where we fill the d orbital of the penultimate energy level, not the ultimate, or in simple words, the valence shell. We are not filling the valence shell. We are filling the penultimate energy level, the second last. Okay, very important. Now, you have always actually, we always take this particular D block element or we call it as transition elements also. Why do we call them transition element? What this word transition means? Remember that if you see the left hand side of the D block element, you will find S block. If you see the right hand side of the D block element, you will find P block. S block are the electropositive metal. P block, when you go, obviously we tend to go for more electronegative. elements, right? So what we are going on is from the electropositive character to electronegative character, or least electronegative to maximum electronegative, or maximum electropositive to least electropositive. So there is a transition from a electropositive element to electronegative element when we move through this D block elements. So there is a transition, there is a change which is taking place. Okay, when we move from one element to another through this D block element, as a result, these D block elements are known as transition element, where we actually go from the most electropositive element to the least electropositive element in the P block elements. Okay, so that's why they are also known as transition elements. And if you see this D block, you'll find out that in one there are 4 series. Okay, so you can see scandium to zinc is one series. Okay, then zirconium to actually cadmium will be another series, then lanthanum to mercury will be another series, and finally the last series. So there are 4 series, and in each series you will have 10 elements, since D orbital can take 10 electrons, so we'll have 10 elements. And remember that a total of 40 elements you will get in this transition elements. Okay, so in D block you will have 40 elements. Okay, so now let us try to see the definition of D block element, then we'll come for transition element, and then we'll try to analyze, are they same or they are different. Okay, so the elements in which the last electron enters the d orbital of the penultimate energy level, as I have mentioned, that is n minus 1. N is the last shell, so we are filling the penultimate, second last, so n minus 1, one less than the last. Okay, are called D block element. For example, like Fe, you can see 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. See, 4, it is the last. What we are filling? 3d, n minus 1. Like zinc, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. See, 4, then you are coming for 3. Okay, that is why we say n minus 1 d orbital. Okay, you are filling the d orbital of the penultimate energy level. Now, the next important question is, what are transition elements? Now, as I have told you, D block elements are generally called transition element. But remember one thing, transition element and D block elements are two different things. Okay, they are not same always. Sometimes they may be, okay, in most of the cases they are, but in some of the cases they are not. So what is the exact definition of a transition element? A transition element is one, okay, whose element in ground state, in normal neutral state, that is what we mean, or in one of its common ion. Okay, every system will have some common ion. In its common ion, 1 or 2 common ion, if it will have incomplete d subshell. Incomplete d subshell means having electron from 1 to 9, not 10. Okay, so it must have electron in d orbital, no doubt, it is a D block element. But if the electron is fully filled, if it is a D10 configuration in its neutral as well as in its common ionic state, common oxidation state, then such elements are not regarded as transition elements. Okay, and if you go with this definition of transition element, it will exclude 3 elements from the D block elements, and they are zinc, cadmium, and mercury. Remember that zinc, cadmium, and mercury are nothing but D block elements, but are not transition elements. Okay, so remember that zinc, cadmium, and mercury are not regarded as transition element. Why? Why it is so? So let us try to see in our next session. So that's what. So all transition elements are D block elements, no doubt in that. Okay, so all transition element, whatever transition elements will be there, it will have electrons from 1 to 9, incomplete D subshell. But remember that all D block elements are not transition elements. Okay, and what I have told you is there are 3 actually common examples of this, and that is what actually we will be trying to understand over here. Okay, so let us try to take it in this way. Okay, so what we'll try to do now is we'll try to understand that what are the elements which are considered as the transition elements. Okay, but they are not, or they are D block elements but are not transition elements. Okay, so what are these particular elements? So to understand that, let us try to see the 3 examples which we'll have. Okay, this does. Okay, so let us try to take, let's say zinc. Okay, I hope you can see in the screen. So zinc is configuration. If you write, it is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d10. That is the configuration of zinc, atomic number 30. Okay. Now, if you see zinc, okay, 3d10, can you see that in this zinc, if I draw that d orbital, okay, the 5d orbital which we have, and fill the electron 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So can you understand that they actually does not have any half filled or incompletely filled d subshell? All are completely filled. Can you see all are having 2 electrons? Now try to understand when we have Zn2 plus. Now Zn2 plus is one of its common ion. Okay, zinc shows one oxidation state, that is Zn2 plus. So let us write its configuration. So it will be 1s2, 2s2, 2p6. Then it will be 3s2, 3p6. I have to remove from 4s. It is the outermost shell. So 3d10. 4s2 will go out, right? Zn2 plus. So still it has 3d10. So still the configuration will remain same. So does it have any unpaired electrons? Does it have any incompletely filled d subshell? No. That's why zinc is not considered as transition element. But no doubt it is a d block element. It has electron in d orbital, but it does not have incomplete d subshell in its common ground state or neutral state, or in one of its common ionic state or in oxidation state. So that is the reason why zinc is not considered as transition element. Let me take one example of a d block element as well as it is a transition element. So we have a transitional, it is a transition element also, and it's a d block element. Like copper. Okay, copper has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. It has an exceptional configuration. Remember that. Now, copper in its ground state, in its normal state, has 3d10. So it will be same like this. So it will have completely filled d subshell. So if you see only the ground state of copper, copper should also not be considered as a transition element. No doubt d block, but should not be considered as transition element because it has fully filled. But the definition says in one of its common ion, it can have actually incompletely filled subshell. So let us try to see. Copper has 2 ion, one is Cu plus, that is cuprous. Okay, so let us try to see. It is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. I have to remove one electron, so I am removing from the outermost, that is 4s. Okay, so 3d10, still 3d10. So Cu plus if I take, then it will not be considered as a transition element, still fully filled. But copper has 2 oxidation state, it has Cu2 plus also. If I write the configuration, that is 1s2, 2s2, 2p6, 3s2, 3p6, and 3d9. One I have to remove from 4s1, another one I am removing from d. So as a result, now I have 3d9. Now 3d9, if I draw it, okay, so what I'll get is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So can you see over there that you have one unpaired electron? That unpaired electron actually fits into the definition now, that a transition element is one which should have incomplete filled d subshell, that is 1 to 9. It has 9. It has one unpaired electron, and no doubt it is a d block element, but now will be considered as transition element also. That is why copper is considered as a d block element but not a transition element. But zinc is considered as a d block element but not a transition element, but copper is considered as d block element as well as a transition element. It fits into both the definition, but zinc will not fit into the definition of transition element. Similarly, if you do for mercury and cadmium also, you'll get the same thing. In mercury, it actually, in cadmium, it will be 4d10. In mercury, it will be 5d10. Okay, and all of them will show an oxidation state of 2 plus. So that's why they were not considered as transition element. So again, I'm repeating it. All transition elements are D block elements, but remember that all D block elements are not transition elements. So that is how we can understand, okay, the difference between D block elements and transition elements. Okay. So now coming for the next. Okay. So let me go for the next. That will be electronic configuration. So what will be the electronic configuration? So if you see this element, these are the 40 elements, D block elements. You can see clearly over there that you have 3D14S2. Can you see the configuration? Argon is the inner configurations. Okay, so it will have a configuration of argon. Then it will be 3D14S2, that is scandium. 3D24S2. Okay, 3D34S2. You can see. Okay, then in similar way you will have 4D45S2. 4D55S2. Then for the next, if you see in the third series, you will have 5D and 6S, and in the fourth series, you will have 6D and 7S. So basically what is happening in the valence or the last shell, you will have the last shell as S orbital, okay, and inner to it will be D, and it will always be 1 minus the last, n minus 1. So how do we write the configuration is n minus 1D. So you can see in all this, the last shell, if it is 4, the inner one, the D, where D is present, is 3. If it is 5, it is 4. If it is 6, it is 5. If it is 7, it is 6. So it is always n minus 1D, 1 to 10. So it will take electron from 1 to 10. And in NS, in your last shell, you will have either 1 or 2. Okay, so that will be the general configuration of D block elements. Coming for the next, oxidation state. Now, just now I have told you that the electrons present in d orbitals are distributed in s orbital and d orbital. Okay, remember that the difference between this s orbital and d orbital is very less. Okay, the difference in the energy. As a result, the electrons from d as well as s can participate in bonding. Means both can be taken out. As a result, transition element shows variable oxidation state. So why it is so? Because the difference between the energy between n minus 1d, the inner d orbital, and the outer s orbital is nearly very close. Okay, so both can participate, both the electrons, even the inner electrons are taking part in bonding. Okay, which is very rare, right? Inner electrons will not take part in bonding, but in this case, inner electrons do take part in bonding. As a result, it can show many oxidation state, variable oxidation state. Okay, so remember that. One such example like iron. Iron shows 2 oxidation state, +2 also, +3 also. Why? Like iron, Fe, the oxidation state is this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Iron is 3d6. Now, if I'll take Fe2 plus, I have to remove 4s2. So you can see in that 4s2 is not there. So what is the configuration? 3d6. But remember that this d orbital can also be taken out. Okay, and Fe2 plus can give 1 more electron and can convert to 3d5. Why it can convert to 3d5 easily? Because when it goes for 3d5, it is exactly half filled. So when it is exactly half filled, it will become more stable. So as a result, the d orbital also participate, and that 3d6, one of the electron will be given and it will be converted to 3d5. As a result, it will show Fe2 plus also, it will show Fe3 plus also. Okay, and remember that it will prefer to show Fe3 plus because Fe3 plus has a stable configuration. That's why iron converts very easily from Fe2 plus to Fe3 plus. This is one example. All the elements actually shows in this D block element show this kind of variable oxidation state, not one oxidation state, but many. Okay. Coming for the next, transition element act as very good catalyst. Okay, if you have actually, if you try to see the various reactions, okay, in organic reaction, if you do hydrogenation, we use nickel as a catalyst, platinum, okay, palladium. In case of Haber's process, we use iron. In case of contact process, we use vanadium pentoxide. In case of Oswald process for preparation of nitric acid, we use platinum or rhodium. All these are transition elements. Now, why transition elements are taken as catalysts? What is the reason behind it? Remember that one of the reason is because of the presence of that unpaired electron. The definition of transition metal tells us that they must have unpaired d electron. This unpaired d electron actually have the possess. When they have this unpaired d electron, what will happen? They will possess the capacity to absorb energy and re-emit that energy. And when they re-emit and absorb this wide range of energies, then that energy can be actually made use in the form of activation energy. Okay. So as a result of which the reaction becomes easier to take place. Okay. In the presence of such catalyst. Okay. That is one reason. The second reason is, remember that just now what we have discussed, because of the variable oxidation state, what will happen is it can easily form intermediate. Okay, that is what actually is the intermediate theory also. Okay, as a result, what will happen is the reactant can easily react with the catalyst, forming intermediate of lower activation energy, and that can be taken into product very easily. Okay, and the third reason is they provide a large suitable surface area. Okay, and as we know that if it is acting as a surface catalyst, surface area, more the surface area, more will be the adsorption of the reactant and better is the catalyst. So they provide a large surface area in which adsorption can take place very easily for the reacting material. As a result, it acts as a very good catalyst. Okay, coming for the next, most of the transition metals are colored. Okay, remember that most of the compounds which they form, like one of the very common compound of transition element which we use is copper sulfate, CuSO4, a blue color crystal, right? Very good colored. So most of the compounds of transition elements are colored. Now what is the reason? Now the color is due to the again presence of that unpaired electron, and remember that it is the excitation of this unpaired electron from the lower d orbital to higher d orbital. That is what we call as dd transition. Remember that whenever transition metals comes in around, actually, or when it comes, or when it is surrounded by the ligands, or when it comes in the field of a ligand, okay, as a result of which what will happen is the d orbital in the metal splits up. Okay, it depends upon whether it is forming what type of complex. Two of the splitting diagram I have shown there. One, the left hand side is for your octahedral complex, the right hand side is for your tetrahedral complex. So what happens in this class of compounds is once this ligand approaches the metal ion, the d orbital of the metal ion splits into two sets. Okay, in case of octahedral, we call it the lower energy level, we call it T2G, the higher one we call it EG. In case of octahedral, the lower one we call it E, and higher one we call it T2. As a result of which what will happen is now there will be two sets of d orbital, and if there are unpaired electron in the system, then the electron from the lower energy can jump to higher energy orbital, as a result of which when energy is transmitted, then the energy usually which is transmitted is in the visible region. Okay, so the transmitted or the complementary color which we usually see is will be in the visible region. Okay, so as a result what we can see is colored. So remember that this transition usually is possible by absorbing light in the visible region. Okay, so that transition, once it takes place from the T2G to EG or E to T2, okay, in octahedral or tetrahedral complex, then this transition actually, once it takes place and once the energy actually or the complementary color is radiated, that complementary color comes in the various actually region of the visible spectrum, and you can see different colors. Okay, so the basic answer is DD transition. Okay, now coming for the next, that is transition metals and their compounds generally exhibit paramagnetic character or paramagnetic behavior. I have already told you that whenever we talk about paramagnetic behavior is due to the presence of unpaired electrons. If you have unpaired electron, the system behaves as paramagnetic in character. And the magnetic moment can be easily calculated for such type of substances, that what will be the magnetic moment of that particular substance which is actually showing this paramagnetic character, and which can be done by a simple the spin only magnetic moment formula, which you can see in your screen, which is nothing but mu, which is magnetic moment will be root over of n into n plus 2 bm. Bm stands for Bohr magneton, which is the unit of the magnetic moment. Now, how to calculate it? Just one small example I'm showing you over there. So for example, let's say we have to calculate the magnetic moment of Cr2 plus ion. So what basically we need to know that how many unpaired electrons are present in Cr. For that, I'll write the configuration of Cr2 plus, which you can see in the screen. Okay, once I write the configuration of Cr2 plus, which is 3d4. Now 3d4, if you arrange in 5d orbital, you'll have 4 unpaired electrons. So the number of unpaired electron is 4. Once I know that, then I'll put that value of n. N is nothing but the number of unpaired electrons. So I'll put the value as 4. So 4 into 4 plus 2, which will be 4 into 6, which will be root 24, which will give you 4.90 Bohr magneton. So that is how I know that how much paramagnetic character it shows. Higher the value of magnetic moment, more is the paramagnetic character. Lower the value of magnetic moment, less is the paramagnetic behavior. If magnetic moment comes out to be 0, this type of systems are not paramagnetic, they will be diamagnetic. If this magnetic moment comes out to be 0, that means unpaired electron has to be 0. If the system does not have any unpaired electron, it goes for diamagnetic character. So that is how actually we can understand why transition metals exhibit paramagnetic behavior. It is due to the presence of, again, that unpaired d electron which they have in their system. Okay, so that is how we can understand the general trends and behavior of transition metal. What are transition metal? What are d block elements? And what are the various characteristic properties of transition elements? Okay, so that's all for this particular video. So thank you, everyone. Do subscribe for this channel for explanation on various topics in chemistry. Thank you.